All right, hello and welcome back. Thank you for tuning in. If you're joining us on Twitch, welcome. And if you're joining us on YouTube, thank you for watching. So today is the 1st of November, one of my favorite months. And today we will be talking about physics, Physics 1 in particular. So without further ado, we're just going to jump into today's content. Not too much to talk about today, but as you can tell by the title, we are talking about work. Interesting topic. So, disregarding physics for a moment, I'm sure many of us are familiar with what work is. It's what we have to do seemingly all the time, something that never stops. Either you go to work and you do work for a company, or you have homework to do. It feels like it never stops. But in physics, work is obviously quite a bit different. So today we'll explore that, do a couple of practice problems, and yeah, today should be a pretty chill lesson. Let's just jump into it. It's not much to go over today, but as always, we'll just cover like the definition. So what is work? Work is simply the product of the force component in the direction of motion with the distance through which the force acts. So I will explain the drawing here, and we'll take a look at the equation. We'll get back to the drawing in just a moment. But work is equal to the force multiplied by this lowercase d, which is going to be our symbol for distance. It can also represent displacement, depending on how the object moves. But if it travels in a straight line, then yes, this would be displacement, because the difference between distance and displacement is displacement measures the straight line distance between the start and end point. So d is our variable for distance, and then we multiply that by cosine of theta. Interesting. What's cosine of theta, you might be asking? And that's a very good question. And to explain that, we'll take a look at the diagram. So let's just say we have some block, and we're applying some force on it at this angle. And perhaps the block is on the floor, something like this. I'll just draw some floor, and we're dragging it along the floor. So the direction of motion is to the right. It just drags along to the right. It's not going up or down, it's just going to stay along towards the right. So work is equal to force, so we would take like the magnitude of this force vector, multiply it by this distance d, so this is like the start point of the block, this is the end point of the block, so we would take that difference and get d, and we multiply it by cosine of theta. Let's just zoom in here. So in this case, theta is the angle between, in this case, the horizontal, which is this, and our force here. But really, theta should be defined to be the angle between the vectors of your direction of motion and your force vector. It just so happens that our direction of motion is parallel to the ground to the right, so theta is appropriately defined to be the angle in between these two vectors, something like that. And we take the cosine of theta, because if we were to just draw down this perpendicular force, then we can break it up into components. So this is like Fy, this is like Fx, and if we take cosine of theta, we get that's equal to Fx over F. So this is equal to, or Fx is equal to F cosine of theta, right? And that's really the vector we care about, because notice how Fx is pointing in the same direction of the motion of travel. We care about the motion of travel because that's where the block is going. So it would be helpful to take the component of force that's pointing in the same direction as the motion of travel. And we do that by splitting it up into its x component and y component. And you might be like, okay, well, what's going on with the y component here? Why aren't we really accounting for that? Like we solved for fx, but what about fy? And we'll explain that in just a moment. But this is sort of where the cosine of theta derives from. It's extracting this this one part of the force vector that's in the same direction of motion. So make sure theta is defined to be, I'll write it out because it might be helpful. Theta is the angle between the force vector and the vector for the direction of motion. Something like that. So not always with the horizontal, just with the direction of motion. And we'll briefly analyze the units for work because we now have a new physical quantity. We should be able to be familiar with the units. And it's pretty simple, right? So force is measured in newtons. Distance is measured in meters, the SI units. Cosine of theta, that doesn't really have any units to it. It's just a value. So if we multiply those units, we get newtons times meters. So we actually say that the units for work are Newton meters, or N times M, or more commonly used is what we call the joule, named after Mr. Joule. I forgot what his name is, his first name is. But yeah, that's how you spell joule. And we use the capital letter J to represent units for work. Cool. So let's take a look at this picture here. It's not much to go off of, but I'll explain what's going on. So we have this person who's walking, and this green arrow represents the direction of motion. So in this case, the person is walking to the right in terms of like the picture. And they're carrying a suitcase. So without considering what's going on with the blue arrow, let's just consider what are the forces that are going on in this picture. So we'll just assume that the person's walking on some sort of ground, and obviously there's a gravitational force for the person. There's Fg, and if they're on the ground, there's some normal force, that's Fn. And I mean, maybe there's like friction between their feet and the ground or whatever, but like, is that really important? No, not really. So, and there's no tension or anything like that. But now we take a look at the suitcase. The suitcase also has Fg pointing down, but then the person's also holding on to the suitcase. So there must be some sort of opposite force to Fg, because if there wasn't, then the suitcase would be accelerating downwards, and we know that the suitcase is likely not accelerating. We'll just make that assumption. So there's some sort of like pulling force, and that's kind of the force that we're curious about here. And we're asking how much work. So the question is, how much work is the person applying to the suitcase? Now, I'm just going to spoil the answer, and then we'll explain why that's the case. Amazingly, the person is applying no work to the suitcase. And I remember the first time I heard that, I'm like, that makes absolutely no sense. And even till this day, it kind of still doesn't make sense, but when you look at it mathematically, it explains why. So, our answer will just say it's 0, but let's take a look at why that's the case. Well, we know that the work of, I'll do work subsuit for suitcase. By formula, this is equal to force times distance times cosine of theta. Okay, so the force is equal to the pulling force. The distance, that's a little bit confusing, so we'll leave that as d for now. Now the point of interest is cosine of theta. Theta is defined to be angle between the direction of motion and force. we said that the suitcase probably isn't accelerating in the y direction, right? It's just, in terms of the y coordinates, it's basically stationary, which means that this person holds the suitcase at the same level at all times, which is a fine assumption to make. Like, sure, they might bring it up and down just a tiny bit, but there's no, like, significant acceleration in that direction, which means that the direction of motion for the suitcase is to the right, because, let me just make this a little bit thicker, something like this. Actually, I don't even want to use this color. But we can see that the direction of motion for the suitcase is to the right because it's going with the person. The person is bringing it along for the ride. And if we take a look at the force in question, it's the pulling force by the person. So that's this force here. Okay? So I've enlarged the important forces. So what is theta? Theta is the angle between these two forces. Whoops. Why can't I do this? It's the angle in between these two forces. And they're basically perpendicular to each other. So in this case, theta is equal to 90 degrees. Okay, well, we need to take the cosine of theta. Cosine of theta is equal to cosine of 90 degrees. That is equal to 0. So when we go back to here, fd times cosine of theta, we sort of just like forgot about d for a moment, but now we know that cosine of theta is equal to 0, so no matter what fp and d are, the total amount of work done by the person on the suitcase is 0. Crazy. So this all comes down to finding the appropriate angle between the forces and the direction of motion. Very critical that we understand how to do that correctly. And yeah, it seems a little counterintuitive, but that's just how it works. So yeah, we're already set to do a couple of questions, so let's do it. If you've seen some of our previous videos or tuned into one of our lectures about a couple of weeks ago, you might be familiar with this diagram and maybe this question because we did something very similar to it. So just to refresh our memories, this reindeer, who doesn't have a name but does have a red nose, so I mean, it might be Rudolph, but okay, doesn't matter too much. So this reindeer pulls on a sled at an angle of 20 degrees above the ground with a force of 60 newtons. The sled is pulled 25 meters on the flat ground. How much work does the reindeer exert on the sled? Okay, so we are curious about what the amount of work is. And, okay, let's just draw the horizontal here. Looks something like this. Obviously, like the sled is touching it. And then the angle between like how the reindeer pulls on the sled and the horizontal is equal to 20 degrees. 20 degrees. And I'll highlight that this is like the pulling force of the reindeer on the sled. And we know that that is equal to 60 newtons. It's given to us right here. What else are we given? We're given that the sled is pulled 25 meters on the flat ground. So that's good to know. The sled's not going up and down or anything. So we'll just say that this is equal to like delta x is equal to 25 meters. Okay, and we need to figure out how much work is done. So work is equal to, by our formula, f times d times cosine of theta. Well, we have a value for theta, we have a value for force, we kind of have a value for d. We have delta x equals 25 meters. Is d the same thing as delta x? Generally speaking, no. And I explained that previously. D is measuring distance, delta x usually measures displacement. It's just sort of the variables we choose. But in this case, it's going to be the same thing. We're given that the sled is pulled 25 meters on flat ground. It doesn't give us any description of the path that it takes. So we can just say that, okay, it travels in a straight line. So in fact, 25 meters also equals d. Okay, so with that, we can just plug it into our formula. Work is equal to 60 newtons times 25 times cosine of 20 degrees. And we want to make sure that that angle is the correct angle. You should be asking yourself, is 20 degrees the angle between the force and the direction of motion? Well, the direction of motion is to the right. That's how the sled is moving. And our force is given by here along the wire. So if we look at the angle between them, yes, it is correct. Theta is the angle between those two. So we're looking good. And you can compute this out. This should be equal to about 1,409.53, and I'll use the units of joules. So that's just a pretty simple question, plugging stuff in. But it's important to, the thing here is you want to make sure that your angle is correct. In this case, it was, so we're good. Okay, moving onwards, we'll move to a conceptual question. So, Maurice exerts a force of 25 newtons on a block for 10 meters. What is the largest amount of work Maurice does on the block, and the smallest amount of work? I guess instead of saying does, we can change this to like can do. So we're just going to be analyzing what's the max amount of work Maurice can do and what's the minimum amount of work that Maurice can do. Okay, so we're given that this is the force applied. That's just really bad what I'm doing. Let's use a highlighter. We're given 25 newtons and 10 meters as our quantities. So 25 newtons is our force. 10 meters is our distance. And we know that work is equal to F times D times cosine of theta. So without worrying too much about theta, we know that no matter what the situation is, these forces and distances aren't going to change because that's what's given to us. So we can say that work is equal to 25 times 10 times cosine of theta. So this is equal to 250 cosine of theta. So it still remains to figure out what is the work done, and to do that we need to know theta. So we have, let's just draw it out. We have some sort of block, and it goes for about 10 meters until it gets to some other place, perhaps. So, theta is the thing in question, but first let's analyze theta a little bit. We can say some things about theta, right? We know that if we're talking about radians, it's between 0 and 2 pi radians, or degrees, 0 and 360 degrees, but we're more concerned about what cosine of theta is. And if we remember trigonometry, the value of cosine of theta ranges between 1 and -1. So with this, we can already say what the max and min amount of work that Maurice can do is. Max work occurs, I'll just write it out, occurs when cosine of theta is at its max. So this occurs when cosine of theta equals 1. Because that would tell us that work is equal to 250 cosine of theta just by formula, which is equal to 250 times 1, and that's just equal to 250 joules. Similarly, the min work occurs when cosine of theta is at its min. And this occurs when, well, if we look at our inequality, it's going from -1 to 1. So 1 is the maximum value, which means -1 is the minimum value. So when cosine of theta is equal to -1, because then we get work is equal to 250 cosine of theta by formula, is equal to 250 times -1, which is equal to -250 joules. Okay, we've solved the question, which is great and all, but it would really help to figure out what's going on in these situations. How is work 250 joules? How is work negative 250 joules? Like, what's actually going on? So, let's go back here just for a moment. So when cosine of theta is equal to 1, when does that occur? That occurs when theta is equal to 0 degrees. And cosine of theta equals negative 1 when theta is equal to 180 degrees. Okay, that's helpful because remember, theta is the angle between the direction of motion and the force being applied. So, let's just say that the force being applied is going towards the right. Force applied is F sub A. Okay? So the maximum amount of work occurred when theta was 0, which means that the direction of motion should also be to the right. So, I don't want to use that color. So this green arrow is direction of motion. And this is the max work scenario. And this should be pretty easy to conceptualize. You have like a block moving along to the right and you're just pushing on it to the right, so that way it continues going in the right. You're pushing it in the direction of motion, you're applying work to it. Pretty simple. Okay, what about the minimum work? Duplicate. Okay. So let's just say, okay. Let's say that the direction of motion will stay the same. We'll just say that it's to the right. So that might, it doesn't really depend on what our force is. A block can be moving towards the right and we can have a force pointing in any direction. In this above case, it just so happened that, we were pointing it in the same direction as the direction of motion, so we're chilling. But if you're thinking about maybe a block sliding on the ground, there still is gravity, right? There still is Fg. There still is Fn. So even though those aren't pointing in the direction of motion, there's still forces, right? And, oops, that's not my eraser. And it's a good thing that I mentioned these other external forces, because here the min work occurs when theta is equal to 180 degrees, which means we need our force to be pointing in the complete opposite direction of the motion. So in that case, the force vector looks like that. F applied is in the opposite direction. And this might be a little confusing, how can Maurice be pulling on the block or pushing on the block in the opposite direction of motion? And for that, a simple example of what could be happening is friction. Friction opposes the direction of motion. So think of this force that Maurice is applying being similar to friction, however that helps you conceptualize it, or you can just pretend that Maurice is just friction. And we can see that, it opposes the direction of motion. Theta is equal to 180 degrees. Cosine of theta is -1, which makes us have minimum work. So these concepts will really help us in the long run, understanding what's going on. I'm sure seeing this in -250 joules for work, that's how can you have a negative amount of work? Well, we just explained what's going on there. Awesome. Let's move onwards. And we're actually going to take a moment to go back to some content and review a little bit more. So, till now, we've talked about work when there's just one force present. So, the force of Maurice in the last example, and the force of the reindeer. But as we know, not every object experiences only one force. In fact, I just highlighted that gravity and the normal force are still present. So just like how when we were learning forces, we were curious about the sum of the forces, or F net, similarly, we're more interested in what the net work is done. And to do that, it's a very similar formula, F times D times cosine of theta, except now we look at the net force, which should make sense. If the previous work examples we just did depended on the force vector, and there was only one force vector, the net force should depend on all of the force vectors. And it does. Now note something about this cosine of theta. Forget all of this for now, I'll get to that in a moment. This cosine of theta is pretty important. Let's just zoom in here. So F net, this is the vector combination, rather instead of combination, let's just use the word vector sum, of all force vectors. Right, so we're pretty used to adding force vectors or just any sort of vector. So F net is the vector sum of all of those. And, well, I don't want to highlight cosine of theta. Theta is the angle between the net force vector and direction of motion, which I'll just abbreviate DOM. Okay? So to use this equation, we first have to find one vector, one total overall vector of all of the forces added together. This is F net is one vector. D is the same, what we're used to. And then for this one vector that we just found, we must then find theta by finding the angle between the net force vector and the direction of motion. Okay, I'll clarify this in just a moment, but let's just take a look at this for a moment. So we have this great equation, F net equals F net times D times cosine of theta, and we know that F net equals ma by Newton and his brilliance. So if we just do a substitution, we put ma in for F net, we get work net equals mad, and we'll just forget about the cosine theta for now, but it's not very important. But yeah, we do that substitution and we get the net work is equal to MAD. And we defined D to be the distance, and generally we're considering like straight lines. And distance is equal to like the final position, I suppose, or the final location minus the initial location. And this equation should look something similar to what we saw in kinematics, where this was like our definition for delta x. So if we go back to kinematics, we might remember this equation. Final velocity squared equals initial velocity squared equals 2a times delta x. So this is what we're looking for right here. This x final minus x initial, and we have that there, which equals d. So let's just put in d into there, and then solve for a. A is right there. If we do that, we get a equals this quantity, vf squared minus v naught squared, all over 2d. And you're like, okay, why are we doing that? It's kind of weird. But this is actually getting pretty exciting. We'll go back to the equation we just had. Work net equals MAD, and we just found this. So let's make this substitution. Put A into there, and we get work net equals mass times this new equation we just found times distance. So we're just plugging this into here where we see the A. And if we do some simplification, we get work is equal to 1/2 m times v final squared minus 1/2 m times v initial squared. And this is something that we call the work energy theorem. And you're like, okay, well, what's energy? And for that, I tell you, hold on just a moment. We will actually be talking more about energy next week, I believe. So this might be a little confusing right now because I just used the word energy and we don't really know what that is. But we'll be exploring this equation in particular a lot more in the coming weeks. This is now just sort of an introduction to see that work will be playing a role in the future, and we have this equation to work with. We don't really need to worry about what this represents at the moment, but now we have a different way of finding work. Instead of F times D times cosine of theta, we have this equation. Okay, let's move onwards. So, a little bit about KE. So I'm briefly going to talk about energy. Like I said, we'll talk about this more later. But this quantity that we see here, 1/2 mv squared, 1/2 mv squared, this is called kinetic energy. And you may have heard about this before, and like I said, we'll talk more about this next time. But for now, the basic rundown of kinetic energy is that this is the energy associated with moving objects. And if you don't know what energy is, that is perfectly okay. We will be covering that shortly. But know that there is an association between something called kinetic energy and objects that move. There are different types of energy, just like there are different types of forces. But that's not important right now. What matters is we have a second equation for work, which we are now going to play around with for a little bit. But first, I'm going to provide you with a much better equation for net work, at least in my opinion. And the mathematical notation here is a little bit strange with the subscripts, so I'll just rewrite it. This is the sum of F. If you're not familiar with this notation, I'll just go over it in just a moment. Let me just write it down. Okay, and this is equal to work net. All right, what is going on here? This is the Greek letter sigma, which represents a summation. So, for example, if I have the summation, something that looks like this, this sigma is the summation. We're summing over all x's, where x begins at 1, goes until 10, and basically it increments by 1. So this summation is equivalent to saying 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, right? We start at x equals 1, we plug in 1 for x, and then we're doing a summation, so we add to that the next value of x. So x goes to 2, we plug in 2, so then we add that to the quantity. And x keeps on going up until it reaches our bound of 10. Until we get there, we add everything together, we get something like 55, right? Okay, so this sigma thingy is just a summation. We're just adding up a bunch of terms. In this case, we're adding f times d times cosine of theta, which is our equation for work. Okay, but what is this? What in the world is going on here? F net we're familiar with. That's the net force. And we know that the net force is composed of individual forces. After all, that's how we compute net force. We take the vector sum of all these forces, right? So this is saying for each force, which is in the net force. So this symbol here, which looks like a funky E, that's the symbol for in. So for each force that we have that composes the net force, we're going to plug that force into here. We're going to take the magnitude of the force, multiply it by the distance traveled, and multiply it by cosine of theta. In this case, well, I'll talk about that in a moment, but we're doing that for each force in the net force. So if the net force has 5 different forces composing it, we're just going to do this, we're going to plug in 5 different forces into here, and we're going to sum them up. Okay, and you're like, this is kind of confusing. Why did you give me this equation? This seems a lot worse than what I just showed you. And I claim that it's actually a lot better. So what's going on here? In this case, theta is the degree, or no, that's not what I wanted to say. This is the angle between the individual force and direction of motion. Okay? And note how I highlighted and underlined individual. The reason for that is every time we plug something into here, when we plug something into here, that only occurs when we're encountering a new force. So it might be gravity, it might be the normal force, something like that. So let's say we plug in gravity. Let's just do a little example. Let's just say F net is equal to Fg plus Fn. So then that's saying this sum, F times d times cosine of theta, is equal to, well, there are two forces that compose F net. First is Fg, second is Fn, so let's just start with Fg. So we plug Fg into this equation, Fg times d times cosine theta. We're substituting it for F, because that comes from there. And then we add to that Fn times d times cosine of theta. Okay? So in this case, theta measures the angle between the individual force and the direction of motion. So here, I'm going to actually say this is cosine of theta 1 and cosine of theta 2, because those thetas may not be different. If you have the normal force pointing this way, and gravity pointing this way, and this happens to be your direction of motion for whatever reason, then this angle happens to be theta 1, and this smaller angle happens to be theta 2. So they may not be the same. So when we compute this equation here, we have to look at each individual force and its angle between the direction of motion. And the reason why this is easier, it is a little bit of work, because, a little bit of work. Okay. What we're doing is we're finding the amount of work done by each force component, right? This right here is literally the equation for work. This is F times d times cosine of theta. And then we add to that another F times d times cosine of theta. The only thing that's really changing is the force that we're looking at. And we're just summing up all of the forces that compose the net force. So these are just a bunch of little amounts of work. And when we sum up all of those little amounts of work, we get the overall net work for the object. We're just looking at it at a force by force basis. And the reason why this is so nice is usually in problems, we can easily figure out what Fg is, what Fn is, what Ff is. Those are quantities we're used to figuring out. It's easy to find those. If we use the other equation back here, we not only have to find all of those forces, Fg, Fn, Ff, we have to be very careful about the angles that they're pointing in. We have to then sum all of those forces together into one supermassive net force, which might be pointing in a really strange angle. Then we have to worry about computing the angle between the direction of motion. That's going to be a really big hassle. Whereas here, we can see that some of these we can sort of just skip some steps. Like Fg is pretty easy to calculate. We know that Fg points down. So if the direction of motion is to the right or to the left, we know that theta is equal to 90 degrees. It's perpendicular. And then we know cosine of theta is 0. So we're just looking at it at a term-by-term basis. And it helps out a ton. And to show why this equation is so much better, let's do an example. So we got Johnny Jambalaya. Okay. Fun story. This is a tangent. I was just helping out my friend with something, and they needed me to join an online call for whatever reason, and they needed me to join in multiple people. I don't know why. So when I joined in the video call, I had to give in a name. So I just made up these completely random names. So one of them was Kevin Syzygy. Another one was Judas Jackson or Ray Lee or something like that. It was just so fun. Bernie Waters was another one, just coming up with these fun names. I don't know. I just thought about that because I forgot that the person I wrote about is named Johnny Jambalaya. Anyways, back to the question. Johnny Jambalaya is mowing the lawn for his neighbor, so seems like a pretty nice kid. He exerts a force of 10 newtons on the lawnmower at an angle of 30 degrees above the horizontal for 50 meters. The coefficient of friction between the mower and the ground is 0.20. The mower has a mass of 3 kilograms. What is the work done by each force? And then what is the net work done? So here we can see that the net work is composed of the individual works for each force. So the first part of the question will find all of those individual works, and then finding the net work will be pretty easy. We just sum those all together. So let's just jump into it. First, let's draw a free body diagram, and we'll take a look from the mower's perspective. So it's on the ground, so there's Fg, as there almost always is. There's a normal force due to the ground. We're given that there's a frictional force, and we'll just assume that Johnny is moving to the right. We'll just use the picture, or rather the mower is moving to the right. He could be moving to the left, but for the sake of simplicity, we'll just say it's moving to the right, so friction opposes motion, so it goes towards the left, okay? And then we have some sort of force that Johnny is applying on the mower, and it's sort of going downwards into the right, so it looks something like this, Fp. And I'll make like this dotted line here, and we're given that the force he applies is 10 newtons, which we won't worry about just yet, but it's at an angle of 30 degrees above the horizontal, which is kind of weird. But if we take a look at the lawnmower here, I'll just sort of draw our forces. Let me use like white, I suppose, yeah. So we have Fg pointing downwards, we have like Fn pointing this way, we have the the frictional force, and Johnny's force is like going in this direction, right? He's pushing downwards on it. And this angle here, that makes sense for it to be, what is it, 20 degrees? I hope it's 20 degrees. 30 degrees, darn. Right, so we can see there that, okay, it's 30 degrees above the horizontal. So all we're really doing is we're taking this vector, and since the tail of the vector isn't at our origin, we're just shifting it there. So I'll just erase that so there's room for this vector. So the vector still points in the direction that Johnny's force is pointing, but now we see that previously the angle was this, that was 30 degrees. So now it's this angle here, that's 30 degrees, that's of interest. So now it's like 30 degrees below the horizontal, but we just get that from geometry. So if we go back to our free body diagram here, we say that this is equal to 30 degrees. Okay, so we have the free body diagram, and it's not a good idea to do this, but I'll just actually disregard that. We're going to show the direction of motion away from the free body diagram. So in this case, we're saying that the direction of motion is to the right. Okay, cool. So we're going to do this on a force by force basis because we want the work done by each force. So recall that work is equal to F times D times cosine of theta. And let's just start with Fg. Okay, so what do we know about Fg? Well, if the direction of motion is to the right, and Fg is pointing downwards, then angle between Fg and direction of motion is equal to 90 degrees. They're perpendicular. And this should make good sense because the mower is traveling on a flat ground. We'll assume the ground is horizontal and gravity points downwards, so those vectors should be perpendicular to each other. And well, from there we can sort of say a lot. Cosine of theta, in this case, is cosine of 90 degrees. And we know cosine of 90 degrees is equal to 0. And that tells us that the work done by Fg is equal to F times d times 0. So that's going to be 0. So there's no work done by the force of gravity. And this should be reminding you of the suitcase example from a couple slides previously, where the person was pulling the suitcase perpendicularly to the direction of motion, and they did 0 work on it. Okay, let's move on to the normal force. The direction of motion is also perpendicular to Fn, right? Normal force is perpendicular to the surface, and the surface is flat, direction of motion is to the right. So this tells us that cosine of theta equals cosine of 90 degrees, which is equal to 0, which tells us the work done by Fn equals F times d times 0, which is equal to 0. So both gravity and the normal force do 0 work. Cool. Now let's take a look at friction. All right. So by definition, friction opposes the direction of travel. This is what we learned. You know, we look at the direction of motion of an object, friction is pointing in the complete opposite direction. So this tells us that theta is equal to 180 degrees. Right, and looking at our free body diagram, it's supported. Direction of motion is pointing towards the right. Friction is pointing in towards the left, 180 degrees. That makes sense. Okay? So what is cosine of 180 degrees? That's equal to -1. So the work done by the force of friction is equal to F times d times -1. And, well, now we have to actually use our values given to us. We don't really have, like, we couldn't just say, oh, everything goes to 0 because cosine of theta doesn't go to 0. So in this case, I'll just put the negative in front. We're looking at the force of friction, and that's being multiplied by the distance traveled, and in this case, we're given it to be 50 meters. So actually, I'll just rewrite this to be -50 times FF. But what's FF? We should remember that FF by formula is equal to mu times F sub n. But then what's F sub n? The questions just keep on coming. How do I figure out what F sub n is? Now we go back to summing the forces. Fn is pointing in the y direction, so we'll take a look at the sum of the forces in the y direction. Actually, I'm going to have to add a page. Okay, so what are the forces pointing in the y direction? Let's go back to our diagram. We have Fn pointing in the y direction, so we're chilling. We have Fg pointing in the negative y direction. All right, but we still got this Fp guy right here. That's pointing at an angle. And when things point at an angle, you should be thinking, I need to break it up into its components. And that's what we'll do. We have Fpx. We have Fpy. We have a right angle. Let's figure out the components. Let's use some trigonometry. Cosine of 30 degrees. This is our angle theta, 30 degrees. Adjacent over hypotenuse. This is our adjacent. This is our hypotenuse. This is equal to Fpx over Fp. This tells us Fpx is equal to Fp cosine of theta. Sine of 30 degrees. Opposite over hypotenuse. Opposite is Fpy. Hypotenuse is Fp. This gives us Fpy over Fp. Therefore, Fpy equals Fp sine of 30 degrees. Brilliant. Okay, so now we know that there are three forces pointing in the y direction. Fn, Fg, Fpy. So if we go back to summing these forces, we get Fn pointing in the positive direction. We subtract Fg. We subtract Fpy, and we know that this equals mass times acceleration. But is the lawnmower accelerating in the y direction? You better hope not, because otherwise you got blades that are flying up and downwards. Johnny Jambalaya should be more concerned about his head being cut off than sweating in the hot sun. So thankfully the lawnmower isn't accelerating in that y direction. We would have some big problems. So this goes to 0. Cool. So we can solve for Fn by saying this is equal to Fg plus Fpy, just by adding those forces to the right-hand side. Fg is your typical mg. Fpy we just solved for, that's equal to Fp times sine of 30 degrees. What's mass? Hopefully we're given that. We are, 3 kilograms. Beautiful. Gravity is your usual 9.8. Fp, are we given that? Yes, we are. He exerts a force of 10 newtons. So we're given that. Sine of 30 degrees is sine of 30 degrees. You can solve this out with your pencil and paper or plug it into your favorite calculator. And this should give you, I'm not sure what it gives you. Actually, 529.4. I'm going to go out on a limb and say this is 34.4. I hope so. Okay. Anyways, so we found what Fn is. Now we have to go back to this. Negative 50 FF, this is what we cared about. This is the work done by FF. Let me just rewrite this actually. This is what we're trying to solve for. Work done by FF, we narrowed it down to negative 50 times FF. We said that FF is equal to negative 50 times mu times F sub n. Now we just figured out what Fn is, and we're given that mu is 0.20, coefficient of friction. So we have everything ready to plug it in. Negative 50, 0.20. Hopefully this is 34.4, but if it's not, the correct multiplication should help you reach negative 328.2 joules. Okay, let me just underline the works that we've gotten. We have one more force to consider, Fp, and we do a very similar thing. Work done by Fp is equal to Fp times d times cosine of theta. This one's a lot less work than FF because we're given Fp, we're given d, and theta is the angle between the force and the direction of motion, which we pointed out here was 30 degrees. So this is just simply plugging things in. May have done some incorrect calculations on my answer sheet. I believe he applies a force of 10 newtons, is that correct? Yes, he does. The distance traveled is 50. And here we're multiplying this by cosine of 30 degrees. This is equal to 500 times cosine of 30 degrees. 4.2, like 8.84, 80, I can't do it in my head. 840 something. No, I multiplied it by 2. 433.01, I believe. Okay. So that's that. So we figured out what the work done by each force is. That was the first part of the question. So now we want to find what is the net work. Work net equals, we have a couple summations, but the one that we'll take a look at is my favorite one. f times d times cosine of theta. And let's just expand this summation. We know that f net is composed of fg, fn, ff, and fp. So we'll just plug those forces in. Fg times d times cosine of theta 1 plus Fn times d times cosine of theta 2 plus Ff times d times cosine of theta 3 plus Fp times d times cosine of theta 4. And you're like, wait a second, we already solved for all of those. That was just the first part, right? Fg, this 0 we calculated, is Fg times d times cosine of theta. Same thing here. Same thing here, Fd cosine of theta, we got this. Same thing here, Fp d cosine of theta, we got that. So we've already solved for all of these. This is equal to 0 plus 0 plus negative 328.2. I should probably be putting units on all of these. Put it on it for one of them. Plus 433.01. We add this all together and we get 104.81. Is this correct? I believe so. 104.81 joules. So that is the total amount of work being done on the lawnmower. Cool, and we see that this equation came in handy. If we had to find the net force, we would be like, okay, this normal force is equal to however many newtons. The gravitational force is equal to like, what is it? 3 times 9.8, so that's like 29.4 newtons. The frictional force is equal to some other amount of newtons. This P force is equal to some amount of newtons, so we have to sum those all together. We'll probably get that the net force points in like some weird direction like that. We have to find a new theta. That would be just so annoying, so annoying. So that's why we break it up. All right, and just like that, we're actually at our last question of the day. So I did say that today's lesson would be kind of short, I think. This question, it's not too bad. It's a little bit annoying, but actually, it's a good question to learn some stuff and see how quantities are related, which is some of my favorite types of questions. Okay, let's read. 1,000-kilogram car is traveling at a speed of 20 meters per second. As the driver hits the brakes, the car skids. The coefficient of friction between the car wheels and the ground is 0.25. How far does the car skid? That's the first part, so we'll just take a look at that. As always, we're going to draw a little picture, and as always, my artistic skills are going to be otherworldly. Bob Ross is going to call me and ask me how I learned to be such a good artist. We'll give it a little window here, and maybe like a little license plate or a tail light, something like that, and then maybe like some headlights here. That does not look like a car. That looks like Mater from the movie Cars. Barely. Okay. And we'll just say it's traveling in this direction. We know some things about the car. We know the mass is 1,000 kilograms. We know its velocity is equal to 20 meters per second. And we know mu is equal to 0.25. Those are our givens. How far does the car skid? All right, so part A. We're sort of trying to solve for distance. Okay, and we'll just say that it skids until it stops. Right? So that means that the velocity final is equal to 0 meters per second, where this is the initial velocity. So already you're seeing that, okay, we have an initial velocity, we have a final velocity, so you might start to think kinematics, and maybe you'd be on the right track. Um, and so instead of going over like the intuition of how you come up with this, I'm sort of just going to tell you what we're going to use because it'll be good practice. We're going to use the work energy theorem. We know that work, the normal equation we're used to is F times D times cosine of theta, right? Which is good, very handy. And it has the D in there, which is what we're solving for. The issue is that we don't really know what's going on with the force. And we can probably try to figure that out, but instead, we've already done questions like that. Instead, I want to use the work energy theorem to show you why we have this theorem and why it's helpful. Okay, so we have two equations for work, which means we can just set them equal to each other and see what happens. So we get, if we do that, 1/2 mv f squared minus 1/2 mv initial squared equals f times d times cosine of theta. Beautiful. All right, so now we have to figure out what's going on with the force, really. And when we consider work, we're really considering the net work, because there's multiple forces being applied. In fact, let's draw a free body diagram. We have the car. It has gravity pointing downwards. It has the normal force pointing upwards. And we have friction opposing it. And if we consider the work done by each component, well, work net equals work Fn plus work Fg plus work Ff. It's pretty easy to see that work Fn equals work Fg, which is equal to 0, because this is our direction of motion by the picture, and Fn and Fg are perpendicular. So I'll just note that because Fn is perpendicular to direction of motion and Fg is perpendicular to the direction of motion. So that means cosine of theta is cosine of 90 degrees, which is equal to 0. So that means this term goes to 0, this term goes to 0. So really the net work depends on friction alone. So work done by the force of friction is equal to Ff times d times cosine of theta. We can solve for that, but let's just go back to here and say that, okay, net work is the force of friction there. All right, well, let's actually get rid of the force of friction and replace it with something that might help us a little bit more, mu times F sub n. And we're like, okay, that still doesn't help, because we don't really have the normal force just yet. Just gonna make this a little bit neater. But we do have a free body diagram. And Fn is pointing in the y direction, so you're probably tempted to sum the forces in the y direction. And you'll notice the car is not accelerating in that direction, which means the sum of the forces should be 0. So this tells us Fn minus Fg equals 0, which tells us Fn equals Fg, and Fg we know equals mg, so Fn equals mg. So just one more substitution, we'll get rid of mu times F sub n and replace it with mu times mg. Cool. So now we have a lot of terms, and you're like, okay, why did we do that? The reason we did that is to simplify it until we have quantities that we know. Like, if we look at it, we're trying to find what d is. If we know what everything else in this equation is, we're chilling. We know what mass is. We know what the final velocity is. We know what mass is. We know what the initial velocity is. We know what mu is. We know what mass is. We know what little g is. And we know what cosine of theta is, because theta goes back to the force that we're looking at. So theta is the angle between direction of motion and force. Which force are we looking at? Force of friction. And we know friction opposes the direction of motion, so theta equals 180 degrees. And now we can just solve for d. So d is equal to 1/2 mvf squared minus 1/2 mv initial squared. All of this over mu mg cosine of theta, right? And let's just do a little bit of factoring. I can factor out this 1/2 m from the numerator. 1/2 mv initial squared. Nope, not quite. And in the denominator, we get mu mg cosine of theta. You notice that the masses cancel. We can bring this 1/2 and bring the 2 to the denominator. So we'll put a 2 here. So just rewriting this, we get vf squared minus v naught squared all over 2 mu g cosine of theta. The simplification from this step to this step is not necessary. The reason I did it is so that way I have a nicer formula. And also, it's nice because we see that the masses cancel here. So we get a better formula that describes the distance traveled. And since this cannot be simplified any further, there's no more factoring or canceling we can do. We know that this distance depends solely on the variables given in this equation. If we just left it at this, we could be like, okay, well, distance depends on the mass. But if we look, we saw that the masses canceled here. And with this equation, there is no mass present, so distance actually doesn't depend on the mass. So now we can do our final substitution. 0 squared minus 20 squared. This is just whatever was given to us in the question. 2 times mu is 0.25. Gravity is still the same. Cosine of theta is cosine of 180 degrees. We do this multiplication and we get 81.63 meters. And that's problem 1. Can you use this equation? Probably. I didn't solve it, but I don't see why you couldn't solve it. You have your forces, all 3 of them, and, you can get your work, well, you can't actually quite solve for work, right? Because you'll still be missing that D component. So you'll have to figure out how to do that. And actually the simplest way to do it is you have another formula. So maybe you can't directly use that. I encourage you to try it, but yeah, maybe not. All right, let's look at part B. How far would it skid if the car was 200 kilograms? So now the car, instead of being 1,000 kilograms, it's 2,000 kilograms. And if we look at our formula for distance, we see that it doesn't depend on mass because the mass is canceled. So that means that for problem B, the answer is also 81.63 meters. Part C is asking if it was 500 kilograms, so half the mass. And still, it's 81.63 meters. And you really start to thinking, like, that's kind of weird, right? Because if you think about, like, a truck that starts skidding and, like, just a tiny car that's skidding, like, why would they skid the same amount? But it actually checks out. So that's pretty interesting. D. This is asking, what if the car was traveling at 40 meters per second? So we'll just assume that this is the initial velocity. V initial. Okay? So we can, we can recompute this out. We can take this formula and recompute it out. But it might be easier to just see that, like, in our original calculation here, everything stays the same in the denominator. All of those quantities stay the same. Vf stays the same, but this V naught goes from V naught to 2V naught. We're doubling the initial velocity. So when we square that, this will go from V naught squared to 4V naught squared. So that numerator will multiply by 4. So I'll just write it out. Numerator multiplies by 4. Oops, that's not what I said. Numerator multiplies by 4. Denominator stays same. So overall distance multiplies by 4. And I can compute that out. That becomes what? 326.52, something like that. But the important thing to realize is that how it scales. If we double the initial velocity, the distance scales by 4. I'm actually going to write that out. If we double initial velocity, the distance scales by 4. So we can see that it depends on how the velocity is squared. So if I tripled the initial velocity, we expect the distance to scale by 9, by 3 squared. Let's look at the final question. Now it's asking what if the car was traveling at 10 meters per second. So now we're halving the initial velocity. Initial velocity multiplies by a half. So we expect overall distance multiplies by the square of 1/2, which is equal to 1/4. And if we were to do the math, which I encourage you to do, plug the values back into this formula, you will see that this indeed does get you a quarter of the distance traveled. And that actually concludes today's lesson. Not too many questions on work, but that does not mean that work is not an important topic. It's very, very important. As we start to transition into newer topics such as energy, we will see ideas from work reappear. This formula, F times E times cosine theta, extremely important. The work energy theorem, which hopefully we'll explore next week. I have to check the lesson plan for that. Equally important, has a lot of applications. So we did a few questions which covered a lot of the techniques you need to know for work, but it's also very important to understand the theory behind work, what it means, and how certain physical quantities are related to work. So I'll keep it short for today. Hope you enjoyed today's lesson. Thank you for tuning in to our Twitch viewers, and to our YouTube viewers, thank you for watching us. And as always, we'll see you next time around. Hope you have a good rest of your day, rest of your week, and until next time, take care.